Today's lesson, section 9.4b, we're still in vectors in 3 dimensions. So the main topic of discussion will be these things called direction angles. Now this is new in comparison to 2D vectors. So here if you're given a non-zero vector, so let's say vector A, and has the 3 components, and then there are these angles, alpha, beta, and gamma, in the interval between 0 and pi, so in between those two values, that the vector A makes with the positive x, y, and z axes. Okay. Now if we look at this, and go explain this a little deeper, okay, I've kind of drawn a picture. So this picture is a vector in the kind of like where all your axes are positive for this vector. So I think this vector A that I've drawn will be 3, 9, and 5, I believe. Okay, so all your values are positive. So when you have a vector, and for any vector like this, with each of the axes and the vector that you have, you are creating angles from those vectors and from those axes to the vector. So like from x, you're creating this alpha angle, and it's hard to see because it's 2D paper, so you gotta like bear with me with my picture. From angle and plus, because we've only seen one perspective, it's hard to kind of like see where the angle actually looks. If I was able to rotate this around a little bit, you'd actually be able to see the angle lines moving around with it, and so it'd probably give you a better perspective of the 3D. But since I can't, this is the best I can do. So angle beta is with positive y-axis to the vector, and then gamma is from the positive z-axis to the angle. So these are your direction angles. So they're the angles at which they are attached to your vector that give your vector its direction. Okay, which is why they call direction angles. Now to find those, we use our angle between two vectors, because the positive x-axis, the positive y-axis, the positive z-axis are kind of like vectors, because they start at the origin and then they go in a certain direction forever and ever, but they do have direction and magnitude. So if we use those formulas, we can set up a formula for each angle. So cosine of alpha is the dot product of vector A and vector I, so that's representing your x-axis vector, okay, and then J is representing your y-axis, and then the z-axis is representing the k vector, okay, but they're all taken to the vector of A. And then you're going to take the magnitude of vector A and vector I and so on and multiply them together just like you would for that formula. But there is some simplification that we can do. So let's just look at the first one for alpha, because the other ones fall in the same pattern. So if we took the dot product of vector A and vector I, remember that vector I is just like 1, 0, 0, because it's just one, like it's the unit vector for that one. Okay, so now we don't know the vector values for A, so we just say a sub 1, a sub 2, a sub 3. So when we multiply, though, since I part is the only one that has a value, all the rest are 0, so that just leaves us with a sub 1 as our dot product. So we can replace the dot product of A and I as just a sub 1. Okay? And then if I take the magnitude, now the magnitude of A, we really don't know, but the magnitude of I is 1 squared plus 0 squared plus 0 squared, which is just the square root of 1, which is 1. So basically we can just get rid of the magnitude of I and just say it's the magnitude of A at the bottom, because it's just times 1 every time. Okay? So this holds true for all the other equations, It's just that the 1 is in a different spot. So for the beta, a sub 2 is times 1, and for the gamma, a sub 3 is times 1. So we can shorten up our equations, okay, into cosine of alpha is equal to a sub 1 divided by the magnitude of vector A. And then so on and so forth for cosine of B and cosine of gamma. Okay. Now, one thing to remember here, and it doesn't look like it quite finished my statement up here, but I was going to say these are also called direction cosines. You may see that they're referred as that in the book, just so you're aware that that's another name for these. Okay. So in particular, another thing is that if your magnitude of A is also 1, then that just means the direction cosines are simply the components of your vector A, and so then that's it. And it makes it pretty easy. So here, example 6, they want us to find the direction angles of vector A if our vector is I plus 2j plus 3k. So if I find these, I want to set up my formulas. So that means, using my shorthand ones, my component for a sub 1 is 1 divided by the magnitude of A, and then cosine of B, or beta, is 2 over that magnitude, and then cosine of gamma is going to be 3 over that magnitude. Okay, now we first need to find our magnitude so we can plug those in. So 1 squared plus 2 squared plus 3 squared gives us 1 plus 4 plus 9. That gives us 14. So if I plug that stuff in, I get the following, and then I do my inverse cosine for each of these. Okay, then that gives me alpha as 74.50, beta is going to be 57.69, and gamma is going to be 36.70. Okay? And so those would be my direction angles for this vector. Okay? Here, another little nice thing is that you can write your vector A using direction angles to help you out. So if you want to write it as vector A as the magnitude of A times cosine of alpha, comma, magnitude of A times cosine of beta, comma, magnitude of A times cosine of beta. That would also be another way of figuring out your vector. So a property that's nice for direction cosines is that if you have the direction angles of alpha, beta, and gamma of a non-zero vector A in space that satisfy the following equation. Okay, so if I have those angles, that actually is kind of like a Pythagorean identity, almost. Not quite, but it looks similar. So cosine of alpha squared plus cosine of beta squared plus cosine of gamma squared all equals 1. Okay, so if you have that fact, then let's say we're given two angles. So alpha is pi over 3, beta is 3 pi over 4, and they're both along the positive x and positive y axis. Then they want you to find gamma along the positive z axis, but gamma is an obtuse angle. Okay, so using this formula, we want to plug our stuff in. So remember that it's like cosine of pi over 3 squared plus cosine of 3 pi over 4 squared plus cosine of gamma. Okay, so now I want to plug those values in. So cosine of pi over 3 is 1/2. Cosine of 3 pi over 4 is negative square root of 2 over 2. Okay, so squaring those gives me 1/4. That also gives me 2/4. So then 3/4 plus cosine of gamma. Then I want to solve for cosine of gamma. So cosine of gamma squared is 1/4, and then square root. Okay, so cosine of gamma is equal to 1/2 plus or minus initially, but since you want the obtuse one, remember that cosine that we're looking at in between 0 and pi. So obtuse would mean that you're in the second quadrant. Okay, so then cosine's negative in the second. Okay, so then that +1 is not the one that we want. So if I look at cosine of gamma for negative 1/2 and do the inverse of that, okay, gamma should be 2 pi over 3. And I found my angle. Okay, so that's kind of the new thing with direction angles and what we can do with them. Okay, so have fun.